Good afternoon, folks. For those who have logged in a little early, we're about 5 minutes away from starting. Just a reminder to please have your microphones muted during today's presentation. Just avoids any background noise for our presenter, and we'll get underway in about 5 minutes time. Thank you. Hi again, everyone. We're about 2 minutes away from starting, so if I could just ask everyone who's already logged in, if you could please mute your microphone just so we can avoid any background noise, and we'll get underway in about 2 minutes time. So thank you for joining us, and we'll be starting in about 2 minutes. Thank you. Good afternoon, everyone. I think we're going to get underway. We'll likely have people join as we go. Good afternoon, and my name is Lanny McGinnis. I'm President and CEO of the Manitoba Home Builders Association. And on behalf of our event sponsors, the Accurate Technology Group and Federated Insurance, welcome to the first of two MHBA virtual technical sessions being hosted this month by the Professional Home Builders Institute. Thank you all for attending today's webinar. Just before we get underway, a couple quick housekeeping notes. We ask that you all please mute your microphones during today's presentation to avoid any background noise. We are right now hearing a number of you with your microphones on. You may not be aware of that, so if you could please mute them, it's most appreciated. And during today's presentation, if you have any questions, please share them using the chat function. It's the chat box at the bottom of your screen. We'll be monitoring the chat, and we'll raise the questions as they come in. So thank you for your cooperation, and encourage you to share any questions you have throughout the presentation. And now to kick off today's session is a quick introduction of today's speaker, Darrell Paul, by our event sponsor, the Accurate Technology Group.
Good afternoon, everyone. My name is Elizabeth Rosenberg from the Accurate Technology Group. ATG is proud to sponsor today's webinar, and it is our pleasure to introduce today's speaker, Darrell Paul. For over 40 years, Darrell has been involved in residential construction, supervising, and today running Qualistat Building Performance Consultants. Darrell has partnered with the VT Group to provide package design and diagnostic services, including hydronic and mechanical engineering design, NECB and 9.36 energy compliance, energy efficiency, and of course, building envelope design and residential wood frame multifamily projects, including engineering services. With offices in Calgary, Olds, Edmonton, and Nanaimo, BC, they also perform diagnostic testing for forensic and warranty claims. Darrell has spent the past 20 years in building envelope and taught the SAIT moisture control course for 14 years. He has lectured throughout Canada on performance-based envelope designs. The third edition of the Building Envelope Tie-in Details book, written for the Siding Contractors Association of Alberta, will be available shortly. Welcome, Darrell.
Thank you, Darrell. Thank you for that, and I will pass it off to Darrell now.
Good afternoon, everyone. Hopefully everybody can hear me. I think I unmuted my computer.
I got it.
We're good. All right. So today we're going to be discussing, and let me bring this screen up here. Today we're going to be discussing the envelope. Second here. Show screen. And as we get into this presentation this afternoon, what we want to get across today is, some high performance characteristics of the building envelope. So, what causes failures, what causes problems, and kind of a little play on words in the title there. Failure to drain the rain on the second plane causes pain on the planes. So the second plane of protection is a critical detail that a lot of times we don't think about. It interfaces with the flashing, interfaces with penetrations, openings, windows, soffits, all sorts of things. So we wanted to get a view on specifically what we look at when we're talking about the first plane of protection, second plane of protection, but how it ties into the rest of the envelope in the building. So what we're going to provide for you today is an overview of a couple of things here. First of all, some of the good principles, good building practice that will provide good performing wall assemblies. We'll talk about the first and second plane of protection in relation to what the building code asks for. We'll talk about the 4 Ds, which you may already be aware of. A little bit of building science, some assembly options, practical applications, And then, of course, case studies, examples of what happens when things go south, when things go sideways, when you have those catastrophic failures or even minor failures. I put my Instagram account on here for Qualistat simply because we use this a ton on site. We have a lot of videos, a lot of information on, different aspects of construction. And so on there, you'll be able to use those when you're on site. Somebody says, well, why do I have to do it that way? Well, let me give you an example of why you have to do it that way. So there's lots of information on that. In terms of, wood frame construction, the question always comes up, why do some wood buildings perform and others don't? Well, what do we mean by that? Well, if you look at this building, this is in Japan. It's considered the oldest wood structure in the world. It's built 1,400 years ago, and look at it. A wood structure that's 1,400 years old. Is that possible? Well, there you have some living proof. Here's another example. This is a wood structure that's 6 years old. And you can see in this wood structure that the OSB has pretty much completely disintegrated on the wall. So the OSB turns black. It starts to lose its strength, rigidity, and then anything that's in contact with it behind there is going to get affected as well. So in this particular case, there was some failing windows and water got in and got trapped in the middle. Now, if we look at the house itself, whoops, the house is, a two-story house with a walkout. It's got stucco over a house wrap. It's got manufactured stone around the bottom, flanged windows, which were sealed on all four sides, unfortunately. But if you look at this picture, look at the right-hand side here and notice that the window is kind of curved down. This window did the same thing. The lacquer on the wall is starting to delaminate, and you can see over here there's a big crack. So the structure of the building was starting to fail, starting to settle. So when we went out and did the investigation on it, there was basically no sheathing left on the wall. The probes that we put through the drywall into the sheathing to test the moisture level, they were 100% wet. And we just basically went straight through into the stucco. Once the exterior was stripped off, here's what we were left with. So the sheeting was completely deteriorated. It was rotted the first couple of inches of the plates. In some cases, the posts and the beams were completely rotted off as well. But it was interesting when you look at this, how they tried to seal the building. So you look up here and they've sealed the bottom of the windows. They've sealed all the joints on the Tyvek. They've put a liquid applied membrane around the flanges to the OSB. And yet all that sealing didn't help. So my rule of thumb is if you seal water out, you seal water in. And that's exactly what happened here. Down at the bottom, they had poured the concrete and they poured it right up to the stucco, so there was no drainage potential. There was a whole bunch of things that led to this failure. So it was a significant deterioration. So the question always comes up, why do we have so many problems with new construction? Well, what's the difference between old construction and new construction? So if we look at these two comparisons here, the picture on the top, a newer building, it's got all sorts of architectural features. It's got stone, it's got stucco, ephes probably. It's got a flat roof. The bottom one, it's been around for 100 years, still standing, might not be the most comfortable thing. But when you look at those 4 points there, which one's going to have more heat loss? Well, what does that have to do with anything? Well, heat loss is what's required to absorb moisture. You need heat for moisture to be collected. So the one on the bottom is going to have better heat loss. It's going to deal with moisture better. Air leakage, pretty obvious. That one's going to deal with moisture better as well. But the mechanical systems are different. In the older buildings, when we had a fireplace or a chimney that took the heat out of the building in the form of exhaust, it created a suction and pulled air through the walls, which dried up any water or moisture that was inside the wall. And now with our modern buildings, we keep them pretty balanced, or sometimes we even pressurize them, thinking that a commercial building and a residential building are the same when they're not. So that makes a difference. And then the materials, the difference between old growth and new growth. So if we kind of examine a 2x6 wall, and we look at some of the characteristics of a current modern built 2x6 wall, we've got new growth lumber spruce pine fir. We've got OSB sheathing, which qualifies as a vapor barrier, and yet we're putting it on the exterior of the building. We've got house wraps. We've got high insulation values. We're using 6 mil poly as our air vapor barrier. We've sealed all our penetrations really well, and then we put latex paint on. So that's a construction method that we would typically use on new homes. If we compare that to older homes, like the one in the picture previous, we see that we had fir material, which is old growth, so very durable. You know, you could soak those things in water for years, and they just are very resistant to deterioration. We had fir plywood or shiplap, so the air could move freely through, the moisture could move freely through. We used a tar paper. We had very little insulation, if any. Craft back paper at times on our insulation. We didn't seal the penetrations overly well, and we used an oil paint, which actually was our vapor barrier on the interior of the wall. So you start to see some differences here in how this building here with 2x4 walls would perform much better than a newer constructed building from some of those factors that we just looked at. So really it comes down to this key component here. We call that moisture balance. So with moisture balance, we're looking at the amount of moisture that goes in compared to the amount of moisture that goes out. So for instance, liquid. If liquid gets put into the building, let's say behind your cladding, you get water coming in or water down inside the assembly, does it go in at the same rate as it comes out? Are we letting it dry as rapidly as we're letting it enter? Or solid, like snow, vapor, which is relative humidity or humidity in the building. How do we dry it out? Well, we can drain it out. So we give it an opening and a path to escape. We can put air drying in there, or we could use diffusion drying. So we'll examine those two in terms of what's better, air drying or diffusion drying. If we look at the code itself, I think one of the things that we run into is the fact that a lot of people look at their building and go, you know what, the building inspector's been here, it's passed, I'm done, right? The problem with that is you're still responsible to meet the code. So in 2.2.10.9, it says that inspections don't remove the responsibility from you or your trades, designers, or suppliers from meeting the building code. So that's your responsibility.
Well, Darrell, can you please unmute yourself?
Oh, did that just happen?
Just happened, yep. Only
Just,
lost about
okay.
10 seconds.
Sorry about that. So the inspections, if you're doing an inspection and you're relying on the safety codes officer, he's seeing the surface areas, the areas that he can see when he walks through, but he's not seeing all the detail. And so that's where the liability comes in. If you are building and you don't meet the building code down the road, that could create some problems for you if you have some litigation issues or liability issues, even though it might meet the warranty requirements. But when we talk about the building code, the National Building Code, which is either the Manitoba edition, the Saskatchewan edition, the Alberta edition, doesn't matter what edition, it's all basically the same information except for a few minor tweaks. When we look at the wall assemblies that it talks about, you've got the mass wall assemblies like concrete walls where water can just absorb into the materials, doesn't really affect anything. We've got a face seal, which is a single plane protection. So if you painted a rubber coating on your wall, you'd have a face seal. You have a concealed barrier, which is the two planes that we're going to focus most of our energy on talking about, because you've got the first plane and the second plane. And then if we take those two planes, which right now just currently have drainage between them for moisture to escape, and we open up the space between the two planes and put vented air through there, or vent it so the air can move through there, then we have what's called a drained and vented space, or a rain screen. So what are the difference between those two? For the most part, we don't use mass walls in our construction in the prairies, and face seal just doesn't perform very good. So we won't talk about those. When we get into the section that talks about cladding though, 9.27, it talks about minimizing openings and managing how precipitation enters the building. So we've got, wind-driven rain, which is kinetic energy. We've got surface tension, capillarity, where it soaks through tiny little spaces, gravity, and air pressure differences. So we're going to address all of those as we go through this in these next few slides. But the one thing that people often forget is, even though we have a drainage plane behind the cladding, the purpose of the second plane is to intercept the moisture that gets between it and to, it says, dissipate rainwater to the exterior. So we drain the water outboard out to the exterior. So we might have a really good drainage plane on our wall, but as soon as it meets a window, or as soon as it meets the bottom of the cladding, can the moisture that builds up in that drainage plane escape and drain out? And that's where the moisture in, moisture out balance comes in. So if you look at this first plane of protection, the stucco is your cladding. It could be stucco, it could be lap siding, it could be vertical, it could be any number of products. It's not designed to be waterproof. It's designed to deflect and keep water as much as possible from getting behind it. Now, when we look at the first plane of protection here, it starts way up here, right? The roof overhang gives us a certain amount of protection. It deflects the water coming off the roof, keeps it from reaching the upper surfaces. We put flashings above our windows. We put flashings below our windows. We put the cladding on, and all of these materials are designed to kick the water back out. But when we look at that second plane of protection, it does a whole lot of work. And sometimes because it gets covered up, we forget to give it the attention that it deserves. So here we're looking at a drainage plane and an air barrier. So anywhere that we extend the building tie-in materials, like up in the soffits, where water can get into the soffits and drain out, around windows, around vents and openings, that's for drainage, to get the water to go from the upper area to the lower area and keep moving it forward closer to the exterior. But then we put a big piece of house wrap here. The purpose of that is stop the air that's coming through these two joints from potentially moving into this little tiny cavity or attic space. So it can act as both protections. It can act as a drainage barrier or drainage plane and an air barrier or an air retarder. And the second plane falls under 927. So when we get tie-ins, we want to have sufficiently large pieces of tie-in paper to tie in with whatever membrane is going on the wall. So if this is getting a Tyvek material, then we would tie those membranes into it underneath and over the bottom. And then if it's a tar paper, we could do the same thing. But tying these in a way that it deflects the water that gets around these components and carries it back to the surface. And if it's flowing to a next layer, we shingle lap it so it goes from the farthest back layer to the forward layer as it drains away from the building. Now, the second plane of protection starts way up here at the soffitting. So we get it up in behind, because if we have wind-driven rain through the soffitting, it can carry moisture 2, 3, sometimes even 4 inches up past the soffitting. So we want the second plane to be up there to protect it. As it drains down, we get to the flashing and it kicks the water back up. So entry point there, exit point there. Same thing with our windows. We put a Silpan protection. We put something to pick up water in that rough opening. Like you saw in that opening example of those windows that were failing, the water was getting into this rough opening and then it was draining. And as it drains, now down here, we need to pick it up and take it outside. So we have an entry point and an exit point, and we pick that up all the way down the wall. And the higher the wall, the more exit points we want to have so we don't accumulate too much moisture in behind that assembly. Something like a gas line that runs through the wall. How often do you go out to the gas line and you see somebody's put a whole bunch of silicone on the vinyl siding around the gas line? What about the water that's coming down the second plane of protection? That's where you need the protection here. Remember, your flashing is to deflect the water. So nothing wrong with putting caulking there. Ideally, you'd have a bit of a flashing there to kick the water away from that penetration or opening. But down here, you'd want to have a caulking at this location. And then somewhere below, if you have a flashing, it can pick up any incidental moisture and kick that back out to the exterior. So a lot of times these things get installed and we don't even really understand why, what's happening, but it's just done that way. And yet on the other hand, we do some products and install some products that don't perform, and it's because of what we did to the second plane. So for instance, here, the second plane falls under 927.38, and the purpose of it is, it says that the second plane of protection, it has an inner boundary, and then it says flashings to dissipate rainwater to the exterior. So here's some manufactured stone. Here's our flashing. Do you believe that the stone and where this mortar is placed is letting that wall assembly drain? And if you put a window above that area and then a space and then a window on the second floor and then a space and a window on the third floor, and all of those let water in, and you're not giving it a space to drain out, that's where you're getting the failures. How about on stucco? Now with the new hybrid stuccos, a lot of us would put, you know, a flashing on such as this in the lower one, and we wouldn't think about it. We'd put the stucco straight down to it. But now with the acrylic coats on the hybrid stuccos, these stuccos will bond to the flashing. How is this water allowed to drain out? So in some cases, we don't have enough drainage capacity behind it. And that's what the building code is asking for. It's saying if you put the drainage behind there, let it drain completely out and dissipate that water out through the flashings. So what about the first and second plane itself? Well, if we look at the first plane here we have an example of vinyl siding. So vinyl siding is a vapor barrier. So when we put the cladding on, it either has to be open so the air can blow through it to dry it, or it has to be vapor permeable. So in the case of vinyl siding, it's a vapor barrier, but we've got so much opening and so much space that the wind and air can freely pass through and get rid of any moisture that builds up behind it. So it doesn't create any problems. On the other hand, if we were to put something like a tongue and groove material on a wall, if it wasn't vapor permeable already, then we would have to add this drainage plane or this vented airspace behind it, because it either has to be vapor permeable or it has to have air move through it. So vinyl siding is vapor impermeable, but it lets air blow by it. Something like a tongue and groove hardwood, very difficult to get air through it, very difficult for vapor to get through it. So then you're going to have to put an airspace in between. So that would be what you'd call the rain screen. Now, when we look at the second plane, it's got to be breathable. When we say breathable, we're talking about vapor passing through a material. It doesn't need an opening or a hole. It's just breathing through, just like a cotton shirt. It's getting rid of the moisture. And then the second plane has to be drainable, has to be able to intercept and pick up water that gets past the first plane. So that brings us to two types of materials that we can put on the wall. So we have our Tyvek material on the left, which is a non-absorbent. We could use a liquid applied membrane. So either a sheet membrane or a liquid applied would be classed as non-absorbent. And then we have our absorbent material, which is our tar paper. So those are rated in 15-minute, 20-minute, 30-minute, 60-minute. In other words, how many minutes does it take for that material to become saturated? And what's the difference between using both of them? Well, if we look at a vapor permeable material, this one here is a house wrap. And then we, these things are in the way. And then we look at its ability to get rid of water. Oh my goodness. This is, I had this running perfectly before the presentation. Anyway, you can see that the water, if you turn your head sideways, you can see the water building up in the joint here. So the water comes down the wall, and because we've taped the joint, there's a lap that's correct from the outside where water goes down. But from the inside, water running down is going to collect in that gap, and then we put a piece of tape over it, and it holds the water in place. So the water can't dissipate, it can't escape. So now it's sitting in that little pocket, and all the staple holes that are in that material let the water drain back through. So it can have water in contact with the sheathing for a long period of time. So when we look at the two different materials and we look at an absorbent versus a non-absorbent membrane on the wall, the one on the left you know, the Tyvek suit or the spun bonded polyolefin. That material is what we call non-absorbent. So it doesn't soak up water. Whereas on the right, this gentleman has cotton coveralls on. That's absorbent. So just think about wearing those Tyvek suits. If you've ever worn one of those and you get hot and sweaty wearing it, and you go outside and you stand in the wind, how much relief do you get? Not a whole lot, because it stops the air from getting through. Whereas if you had the cotton coveralls, if you're sweating like crazy, it's going to absorb into the cotton. Now you go stand outside and the wind blows across the cotton, absorbs the moisture and takes it away. Now you could do that with the coveralls on the left, but you'd have to unzip them and let the wind blow into them. So there's an example, you know, if that was a house and we had moisture within the house at a higher rate than we could get rid of it, we don't have a moisture balance. That means it's getting trapped in there. So the product on the left is super breathable. The product on the right doesn't protect you from moisture very well, but it'll dry really quick. So each one of the products has its own advantages and disadvantages. So what are the 4 Ds? Well, if we look at the 4 Ds of construction, especially with exterior claddings, they are deflection, drainage, drying, and durability. So let's put these into context. If we look at deflection, if water can't hit it, it can't get wet. In other words, if you go out in the rainstorm and you take an umbrella, for the most part, it's going to keep the rain off of you. Now, it might not keep you perfectly dry because your feet and the bottom of your legs where it's not sheltered are probably going to get wet, but for the most part, it's going to keep the rain away from you. And so deflection is an important principle. When we look at overhangs on a building, for instance, here, if you left your windows open and you lived in the house on the right, if there was a rainstorm, everything in that room would get wet. But on the left, you've got that huge overhang. You're probably not going to see a lot of rainwater enter that building. So a good illustration of how deflection can keep water out of the inside of the building. Here's an example of a drainage system. And this was a water test we did on a house that had some leaky windows. Notice the windows here on the right, they've reinstalled a new window and they put flashing on. Look at the separation that the flashing creates. Water doesn't touch anything on that window at all. So that's what we want to see our flashing do. Now, if you watch as the water runs over the second window, the flashing barely covers the window, but see, when we talk about capillary action or wind-driven rain, water that reaches the joint between the flashing and the window, if there's any kind of inward pull there, it's just going to suck the water right in where we don't want it. So there's an illustration of deflection and how well it performs when we're looking at a building. But again, if we look at this example, deflection doesn't completely eliminate the problem. So here we've got a flashing on a roof, a drip edge flashing, water's coming off the valley. See how the water sticks to the roof, surface tension, and it gets pulled back up underneath and now it's dripping down. So we can't just rely on surface tension alone to eliminate the water. So our deflection also relies on things like flashings. So here we have a flashing to code. Up on the upper section here, we see that underneath the window, there's a reverse flashing because of the flange. We've got a separation away from whatever cladding's below it, so it's not in contact. So when the water's draining down the surface, it causes it to break the surface tension and drip away from the wall. As the water maybe gets inside, this lower flashing right here is designed to pick up that water and kick it out in a way. And then we'll put an end dam on any of our upstand flashings to keep it from moving off the 2 ends of the building where the flashing is. So we'll keep it in the flashing, we'll kick it off the face. It can't go off the ends down the joints on the sides of the window. And that way we can reduce the amount of water going over joints or openings. So flashings were never designed to be waterproof, but we want them to kick water away. An example is, what do you do when you have paper on a building? Maybe it's been papered by the framer. The house wrap's already in place and you need to add a flashing. Well, a lot of people will just slice it and stick the flashing up underneath it. But the risk there is wind-driven rain blowing it up here blows it right onto the interior of the surface. So even when it comes to flashings, having the correct overlap on your house wrap means that wind-driven rain blowing up and behind here is picked up and kicked back down to the bottom. It's not going to end up behind. And if it does, it's going to be such a small amount that that assembly should be able to handle it and deal with it. So again, moisture in equals moisture out. We have a moisture balance. So deflection is a pretty important factor. Of the 4 Ds, deflection, drainage, drying, durability, the next one is drainage. So a little tip on drainage: if water fills in, if you don't let it drain, it's just going to overflow. So good way to illustrate it. Water in should equal water out. If we look at this assembly here, this particular wall has stone on it. It's a manufactured stone. It's a 4-story condominium apartment. And it's been, looks like they've got the peel and stick in place. They got tar paper, but this is a 7-year-old building. So after 7 years, your OSB looks like powder, like dust. So not a lot of protection there. So when you look up from the top, you're getting a significant amount of water entering, but there's no drainage ability there. And if there's no drainage ability to get rid of the water, it just sits there. Here's another example of what happens when you put a peel and stick membrane at the bottom of a window flange. So here the window flange has been sealed to the wall. And notice how much moisture has been trapped inside here. Water that's trying to come out of the rough opening is just sitting in there. So once you pull that peel and stick back, you've released whatever moisture is in that rough opening and let it drain out. So that'll rot that sill out completely. So again, your second plane of protection ends up going from the inside all the way through to the outside. Now, if we look at this example, this is a fairly complex detail here that can fail quite easily. So right here, this section right here is what's being shown in this illustration here on the right. So just imagine on the right here, you've got a reverse flashing that goes all the way along, meaning that the flashing goes in and down. There's no upstand because there's a flanged window in there. Now from this point over, this is still a reverse flashing. So water's going to enter right there and go down here. What's wrong with that? Well, here they've sealed this point to stop water entry, and they've sealed this point for water entry so that water doesn't end up behind the stone, but they haven't sealed this joint here. So now you have water entry there, which goes between and right behind that reverse flashing and right down behind the stone. What's the problem with that? Well, in this application, the stone is going to go down to this lower flashing here. And when they put the adhesive on, it's going to bond to the concrete right here. And whatever moisture is here is going to be stopped right here, and it's just going to build up and come back into the building. So the foundation is somewhere down here. There's a slab or a joist ends are somewhere down here. But because the water can't carry on the paper and flow between the paper and out this lower flashing, it builds up and creates problems. So you want that full drainage. So here we have the siding contractor, we have the stone installer. We're both responsible if this window fails because they didn't address the second plane of protection. Also, when we seal this right here, what about incidental moisture gets behind this on the second plane there? How does it drain out? It doesn't. So this flashing should have been terminated right here so that this could drain and this could be sealed so water couldn't enter. So there's an example of what happens when we don't think about the second plane of protection and how it's going to exit from behind the assembly. Another area that comes up is drainage when we put styrofoam on. So if we've got a fibrous material like a rock wool going on there, no problem. We put our drainage plane right behind it. Water goes through the rock wool, it drains out, escapes, no problem. If we choose to put our rigid insulation, rigid foam over the sheathing, and we choose the second plane of protection to fall behind it, we want that second plane to be able to drain. And one of the big failures that we're seeing nowadays is these hybrid EFA systems where somebody came along and they put tarp or house wrap on here, they put 2 inches of foam, and they put their EIFS coating, their laminate, on the outside surface. And then water got trapped in there. And then the pressure built up and pushed it back into the building. So anytime you're putting a rigid foam, you're better to put your second plane of protection on the outside. In fact, if you go by the code, if you properly detail the joints on this, you don't even need a house wrap on here. You don't need, because this material can act as a second plane of protection if it's the right type of insulation. But if you do end up adding insulation, here's a couple of options. You've got these variety of grooved products that can go on the wall. And that's just going to allow a little bit of moisture to drain back out, prevent it from getting trapped. And that'll stop the pressure that's going to build up in behind there. Other options include things like a Tyvek drain wrap. And you think, well, there's hardly any drainage ability on this material. How is it going to prevent the water? You know, how's it going to allow the water to escape? Well, it's pretty amazing how much that will create, how much drainage ability that will create. It's not for air movement, it's only for water movement. So that'll eliminate any hydraulic pressure or hydrostatic pressure from building up in behind. We have other products such as these dimpled products like this, which have a little silicone dimple on them. And then when you put your cladding over top, for instance, if you're using panelized materials like Hardie's panelized material or other materials that are going to sit nice and tight to the wall, then this will just separate it and give you that little bit of drainage plane in behind. Sometimes you may want more drainage. So you have products like this, products that give you just a wider space. And they'll also provide just a little bit of air that can move through. Depending on where you let air in and out of the wall assembly, you could treat this like a rain screen system because it'll vent that wall cavity. Here we have a water test that was conducted a couple of years ago. And when we did this, our typical method of finding out where the windows leak is we tape off the window frame, poly and tape it, and then we run some water over it with the blower door running. So we simulate a strong wind. So here, if you watch the water, it's running down the surface on the outside of the first plane of protection, but notice now it's starting to leak out right there from the second plane of protection. So obviously there's water behind the stucco and it's draining and trying to escape. But in this case, the windows were sealed at the top. If we just pause that right there, what we can see is at the bottom, these have Silpans. And the Silpans were installed correctly. They were left open and water is able to get in there. So that water is actually in the rough opening of the window. It's on the inside. But because it's collecting the water, it's draining it back out underneath. It's not trapping it and building up a hydraulic pressure in behind there, which will force its way over the overlaps of the paper or force its way through the staple holes. So it was performing exactly as intended. So I thought it was a really good illustration of what we can see when we, start examining windows really closely. Let's see if I can get to the end of this one. Yeah, you can see lots of water draining out from behind that second plane. So if we don't give it a place to drain out, that's where the problem starts. Right there, you can see at the head of the window flashing, there's no plaster stop or casing bead, I guess you call it, that would let the water out between the flashing and the top of the window. So another example, whatever the entry potential, double the drainage. That's our rule of thumb. But even at moisture balance, you're going to let 2 cups of water in, you let 2 cups out. If you let a cup of water in, 1 out, 1 teaspoon in, 1 out, and so on. Our rule of thumb is double the drainage because we just don't want the risk. If that drainage cavity gets contaminated with something, we want it still to be able to drain out and eliminate that moisture. Here's another example of hydrostatic pressures that can be created. So it's not just the foundation that experiences hydrostatic pressures. So here on the left, we're looking at non-absorbent, we're looking at non-absorbent materials. So a non-absorbent material would be something like a house wrap. So if you get water between it and you happen to nail a material on, how will water that gets behind it drain out? Well, the question I always hear is, well, water's not going to get behind here. Yeah, I think so. Yeah, water's going to get behind there. So water's going to get behind there, but now it's going to get trapped, and that's going to build up a pressure, which is going to drive it into the building. Here we have an absorbent, like a tar paper. And the difference is if we put that board on here, then the tar paper can still allow the water to absorb into it, and it'll get rid of that water quite a bit faster, that liquid, quite a bit faster than the house wrap material. Better yet.
Hey, Darrell, sorry to interrupt you there. We have a question from the gallery, Peter
Yep.
Todd. Were
Sure,
those lower windows leaking at the top of the window?
On the previous slide, at the top of the window, they weren't leaking. What was happening was the water was, let me just jump ahead here. So I guess right there, the water was getting trapped. So it wasn't able to escape fast enough. So the weak point in this assembly was the fact that there was more water getting in than was coming out. So the homeowner was getting, water coming in around the baseboards on the main floor of the house. And when we tested it, water was not able to escape out the window head, so it was building up a pressure in behind there. It was overflowing and coming back inside the building. So that was what the problem was. Even though they had Silpans, the water wasn't able to get to the Silpan. It was still trapped within the wall assembly. So hopefully that answered your question. So it wasn't the window head leakage, it was the fact that it couldn't drain. Good question. So back here, non-absorbent, water gets trapped. Absorbent, it can bleed through. Or better yet, we put a control here where we let any moisture that builds up hit that flashing and drain back to the exterior. So these first two examples are examples of what I would say not to do, and to add a flashing here. And if you want to make this flashing even more bulletproof, if you were to tape this flashing to your membrane, now all the water that gets picked up there gets kicked out at that location. So it really depends on your moisture load, how much moisture potentially can enter, and so on.
So Darrell, Peter has a follow-up question. He asks, so the second plain paper kept the water off the wall sheeting?
On the previous video, so right here, the second plane of protection. So right here, I don't know if this will let me draw on the video. Okay, right here. So the water is draining. So this water that's on the stucco right here, that's between the second plane and the stucco. So it's not on the wood. So it's draining where it's supposed to. It's doing what it's supposed to. But as soon as it drains down inside back here, at this point, it's trying to escape and it can't. So now it builds up behind the paper and starts to rise back up because it equalizes. So that's the head pressure principle, right? Whatever the width of or the height of the column of water is, it's going to equalize on both sides. So the paper here, it's trying to drain, it can't escape, so it builds up behind the paper and it comes back into the building. So that could be through staple holes. We only have a 4-inch rise. So you imagine the drainage plane here is probably somewhere around 1/8 of an inch or 1/16 of an inch. It's not huge. So if you had a 1/16 of an inch water rise up in front of the paper about 4 or 5 inches, then when it pushes through, it's going to equalize on the back side of that 4 or 5 inches, which means it's over your paper onto your wood, onto your framing. So that answered the question. All right, I think that, perfect. All right, thanks, Peter. Those are really good questions, by the way. This can be a very in-depth discussion, so keep them coming. Here's an example of what happens when the Silpan is not placed inside of a wall assembly and you have moisture trying to drain out. So here you've got this little wall section here, and there's a window in it. And where the water is draining, it's hitting the window, going into the rough opening, and then draining out. So the issue here is the fact that they put so much energy and effort into the flashings and the detailing on the outside, but they didn't address the fact that the window is going to have water go through it. I don't know if everybody knows the two types of windows, those that leak and those that will leak. So not really, but that's what's going to happen if we let water into the rough opening. And the water doesn't just come from a window through the rough opening. It can from the soffits, it can from another window above it. It can come from a lot of different areas. So Silpan flashings are part of the second plane of protection. Water goes in. In this case, we got a back dam. So the back dam is placed right even with the central glazing of the window. So there's a triple glazed window. In this case, it's sitting directly on that support. We pre-leveled the window rough opening. We put the sill protection of the back dam on there and then set the window right onto it so that the water that gets into the rough opening from the glass outwards is allowed to drain. And we don't insulate that spot. We leave that open to let drainage occur. So same thing with the door. We could put a window into this rough opening as well, put it on support blocks, glazing blocks, and then put a closed cell backer rod at the bottom, put a bead of caulking over it. Boom, you've got a drainage plane, you've got an opening to let water out. You don't have to insulate that cavity. It's a tiny little cavity. And if you compartmentalize it like that at the bottom, you've got more than enough drainage and more than enough insulation from the dead air space that creates. Here's an example of a sample window installation. So here we're putting the primer on the window, or I'm putting the primer on the window. I put a lower sill bib on here, and the lower bib just gets stapled up along the top of the bib. We leave a 1-inch space because I want the peel and stick that I put on the window to connect to that OSB to keep any wind-driven rain out. Then I put the corners on. These are pre-made corners. You can get these through Grace and Resisto, and there's a number of products that are on the market right now. But once you put that on there, you put your peel and stick membrane at the bottom. You put your peel and stick membrane at the top. So there's the bottom. Here's the right side. Here's the left side. And now we're ready to fold the paper into the rough opening. So we've completely protected that bottom sill. Water that gets in there, water that comes off the vinyl window, down the sides, it sits on that Silpan and is directed back out. So there has to be some waterproof protection of the inside of the jamb extension. So that could be a built-in piece of 1x4 or 1x4. A built-in piece of 1x2 or a 3/8 piece of plywood. It can be a closed cell backer rod and so on. So now any of the water that gets into that rough opening is drained to the bottom, and then we leave the bottom open to drain the water back out. So again, moisture in, moisture out, achieve a moisture balance. All right, so we talked about deflection and drainage. What about drying now within that assembly? Well, there's two ways we can dry things. We can dry them with heat and air, and we can dry them through diffusion. Now, the difference between the two is heat and air is going to be way faster, dramatically faster than what diffusion will provide. So as an example, here's I guess it's a roof. So it's a deck over living space. So it's a roof. That's 3/4 inch OSB there that's coming out of there. So the top membrane, the waterproof membrane, is a vapor retarder. Then they've got insulation, and then they get poly on the bottom inside. And again, it's an example of leakage. There's the top chord of the engineered floor joist. But what happens here is the water that gets in there by means of vapor, it accumulates within the wood. The wood just soaks it up and it just gets wetter and wetter and wetter, and it's not drying. So if it's allowed to get wetter and wetter and wetter, in other words, we're absorbing more moisture than we're getting rid of, we haven't achieved a moisture balance. And so the result is things like this, which can be catastrophic. So when we look at the difference between air drying and diffusion drying, air drying is really fast. When you ventilate an attic, if you get water in there, it's gonna vent really, really quickly. If you get drywall wet on the interior of your building, it's going to dry really, really quickly. But if you get moisture inside the cavity in the insulation, you're limited because you're going to end up using diffusion, which means you're back to the Tyvek suit. How do you get rid of the moisture? You got to wait for it to slowly pass through. So diffusion drying, it's slow to let moisture in, it's slow to let it out. So it takes a long time to get rid of that moisture as opposed to air drying. So if we compare different sheathing materials and look at the assemblies and say, well, which one's going to dry better? We can look at the left, and we've got the buffalo board there, asphalt impregnated fiberboard. We've got dense glass drywall, we've got sheathing, and we've got strapping. Which one's going to perform better? Well, with nothing on it, the strapping is going to perform pretty good because the air can blow through it. So then we come along and we put covers on them, because if we have strapping, its breathability is around 500, but depending on how much the wood shrinks and how much space it creates, that can go way, way up. That's when it's first installed. Exterior drywall is about 1300, OSB is 44, qualifies as a vapor barrier. 75 for drywall when it's dry, or plywood when it's dry, 250 when it's wet. So its ability to get rid of moisture when it gets wet goes way up. And then the blackboard, or the fiberboard, 2100, super high breathability. So it's not just the second plane that has to be breathable or the first plane that has to be breathable. It's the entire assembly, those three components on the exterior. So again, if you want it to dry, not only do you have to put really good vapor barrier, or vapor barrier on the inside, really good air barrier and drainage plane on the outside, but your sheathing has to let that assembly dry too. Let's say you put OSB, which is only 44, and you put a Tyvek type material, which is about 1300. You still got to get through the 44 before you ever reach the 1300. So that's why you got to look at the sheathing as well. All right, let's see, what did we miss here? Moisture in, moisture out. Drying ability for walls, when we don't have good drying materials, means we would put on a rain screen or a vented space between the cladding and the sheathing. So right here, you can see it, right? Your cladding is either not very permeable, like a metal, or it's got very little ability for air to blow through it. It's just not going to get rid of vapor very quickly or easily. So we would put strapping on here to allow air to come underneath, go out the top, or vice versa, in the top, out the bottom. It dries it out. So that's an example of how we can really improve the drying ability of a wall assembly by adding these types of materials. Very high drying potential. Here's a tongue and groove wall. They had some air leakage in the tongue and groove wall. And what happens is the tongue and groove swells up. It's basically flooring hardwood for inside a building. You put it on the outside, you let warm air from the inside leak through your wall assembly. If you don't have that airspace to get rid of that moisture, it just sits there and soaks into the wood, and then it turns into a banana. And now you have this defect to deal with, you have to replace. So when you look closely at drying, there's air and there's vapor. And in this case, on the left, you see an example of vapor in a visual, right? The steam coming through, the water is being stopped here. The water can't escape, but the steam is coming out of this pot. So that's an example of vapor being able to escape. And it's the same thing that happens through vapor permeable materials, like a spun polyolefin, like this suit on the right. But it takes a long time for it to go through. A good example would be the difference between a cotton shirt and a polyester shirt. You know, you might like the look of that polyester shirt on the right, but on a hot summer day, the one on the left is going to be far more comfortable because it's more breathable. It'll absorb moisture. When the wind blows, it'll dry it out. It'll stay dry longer. So it's the same principle when we look at our house, on our building. One way I use to illustrate the difference in vapor and how it passes through is to look at something like this. So here we have a window screen. And if we were to look at a house wrap material through a microscope, we would see all these little openings and pores. If we were to look at a basketball or a water molecule, it would look like this. Well, it wouldn't look like this because it's H2O, but it would be about that size. Air molecule would be about this size, vapor molecule about the size of a head of a pin. So if you tried to put the water molecule or the air molecule through the house wrap, you would have to cut a hole to get it to go through. So that's why a house wrap works really good at stopping water and air. In terms of letting the vapor go through, it's like taking the head of the pin and trying to put it through the window screen. You're going to go through once in a while, but every once in a while you're going to hit that screen and it's not going to go through. Now, if that didn't have a screen, if it was solid, that would be a non-vapor permeable. But because it's a screen, the vapor goes through fairly reasonably. If you make the screen bigger with bigger openings, the pin will go through all the time. It'll rarely hit the screen. And so that's one way we can illustrate vapor diffusion. We don't need a hole or an opening. We just need that small, tiny little molecule to be able to pass through to dry it out. All right, so deflection drainage drying. What about durability? Well, durability is pretty simple. It's not sensitive to moisture. In other words, if it gets wet, it doesn't bother it. There's no food source for anything to grow. So concrete, plastic, fiberglass, treated lumber, they can all get wet, but there's nothing in there for it to grow on. So a durable material is another option. If we can't make it drainable, if you can't put deflection, drainage, and drying on it, then we can also use a durable material which isn't bothered. So a mass storage wall, like a concrete block wall where it soaks up with water, you know, that is something we would class as a durable material. No questions? All right. So again, moisture in, moisture out. All right, we're going to shift gears a little bit. We've talked about moisture on the second plane and how to get rid of it, how to dry it, how to deflect it. But just because you have a hole, does it mean water will go through the hole and into your wall assembly? Well, the answer is no. If you had a strong air pressure inside your house on a windy day and it's raining and you opened your window and the wind from the house, from whatever was making that wind, a fan or something, was blowing out the window, how much water, rainwater, would come in? Almost nothing. So that's where this principle comes in, this Mop principle. So moisture, an opening, and a pressure, which is really a force. But we don't get that nice acronym if you go MOF. So moisture, opening, and a pressure, or MOP. How's it work? Well, here we have three components. We have rain at the top, vapor in the middle, and snow on the bottom. So we have those three types of moisture that can move through, in and out of a wall assembly. We have an opening, which is right here. So if there's an opening and we have the moisture, it's just going to pass through, but what's going to carry it? It's this truck or the air that's going to carry it through. So if the air pressure is facing this way, it's not going to go through the opening. If the air pressure is facing this way, it's going to carry that rain and take it through that opening. Hence, we have a moisture, an opening, and a pressure. So if we want to eliminate moisture movement through an assembly, we need to eliminate any kind of pressure because it's hard to stop the rain. Although with the other 4 Ds, we can deflect it and we can drain it, but it's pretty hard to stop it. The opening we can seal to the best of our ability, but even a tiny hole, the pressure will still drive it through. So here's an example. Here's an exterior wall. It has an exterior styrofoam on it. So it's an EFIS wall. So it's got 2x6 wall, R20 insulation, OSB sheathing, 2 inches of foam, and then the lamina or the acrylic finish on the outside. Now, there's no real protection here. There is a strong north wind always hitting this building all the time, every time the wind blows. And rain's always hitting it, but you don't have any deflection. You have this little doorbell hanging off here. So that little doorbell hanging off there, water is going to be in contact with it every time it rains. So water is going to hit this wall, it's going to drain down, and it's going to come in contact with that hole. So if water hits that hole, what makes it go into the hole? It's this truck, it's this driving force or this pressure that pushes it through the opening. For it to go through though, there has to be an opening on the inside as well. So if we have an opening on the outside, opening on the inside, and air can flow through, air will carry that rainwater through into the building. So what's the big deal? Well, if we go back to those 4Ds and look at this application here, we had no deflection. So even a flashing here, right? If we'd had a flashing here, we could have deflected the water away. If we'd have put the doorbell on and put the 2 screws in the doorbell, we would have deflected water away. So we didn't have deflection, we didn't have drainage, we didn't have drying, and we didn't have a durable material. And then we introduced the mop, the pressure that pushes the water through the opening of the hole into the building. So we basically failed on all fronts, unfortunately. You ever crawl in an attic and find a big accumulation of snow? That's about 8 inches deep, big chunk of snow. By the time we got up there, it was a big chunk of ice. So you have an opening, you have a pressure, which is the wind, and you have the moisture, which is the snow. It's going to go through the opening. And if it's really howling and can continue to blow through, there is snow that's going to get in there. So that's where the MOP, moisture, opening, and pressure. Here's a basement. And this is standing on the inside of the basement, looking at the basement window, which somebody forgot open for the weekend, and it snowed. And obviously there was wind, so the wind blew into the basement, and in the wind was snow. So the pressure was the wind, the opening is there, the moisture is the snow. So that mop principle really, really helps us to understand how things work. So look at the door on the left. I think of that mop principle. Door on the left, where is the weather seal on this door? It's right here. So why don't we put a piece of tape right here when we seal up the door? Because we have what's called a pressure equalization. So when we're driving down the highway, the air goes into that opening and it creates a pressure behind it that's equal to the pressure outside of it. Well, if we have an equal pressure, how does the truck carry the rain into the opening? How does the air carry the rain into the opening? It can't. So this is an example of a rain screen system on your house. When you can move the cladding away and equalize the pressure on both sides of the cladding, just like this door, then put the weather seal on the inside, then you're going to have a very high-performing building, high-performing wall. So let's look at it in this example here. We have wind blowing on the outside, so the wind is trying to get into the building. We have rain hitting the surface. We have vinyl siding, so we know that the air is going to get behind it, and the pressure becomes equal on both sides of the siding. But because we've overlapped the joints here and we haven't sealed them, the pressure now is equal on all 3 components. So pressure equal between here, here, and the space behind it means that there's no suction. The air can't get through to push water into the opening and push it all the way to the wood. This is your car door principle. Whereas if you were to seal this joint, let's say you take a piece of tape and you seal this joint, you probably still have some staple holes, but the pressure now behind here becomes negative. So you have a negative pressure behind, the wind is blowing, it's trying to get in, well, it blows around through the siding, so you have an equal pressure on both sides of the siding, so there's no suction of the water that's sitting on the surface, but any water that happens to come in contact with that staple hole gets sucked back into this opening. And so there's an example of pressure equalization and how beneficial it can be or how detrimental it can be, depending on where you put it. So think of the car door. When you think of that mop principle, think of the car door. Moisture in, moisture out. Can it withstand the amount of moisture that's going to get hit with? If you're sitting on top of a mountain where the wind is constantly blowing 365 days a year and it's raining every day, then moisture out has to equal moisture in. If you're down in a valley, you hardly get any rain, hardly get any wind, all the buildings around you protect, all the trees around you protect, you probably don't need a lot of protection on that building. So it really comes down to where you're putting the building itself. So what did we learn today? The first plane, or the cladding is for deflection. It deflects the water away. It keeps the majority of it from getting through and onto the second plane. And so when you look at that in the building code, it asks you to put caulking around the windows, around penetrations, around openings to reduce the amount of water that can get through that first plane and reach the second plane. Now, if it reaches the second plane, what happens? Well, we have the option of an absorbent or non-absorbent. And if we get incidental water that gets trapped between, we'd prefer to have an absorbent material. However, if we're not worried about that and we're not building that way, then a non-absorbent material works just fine. It really depends on the application and the system or the design of the system that you're putting together. Think of absorbent versus non-absorbent on your windows. If you wrap a piece of tar paper into the rough opening in the windows like we did for years and years and years and years, water sitting on there will soak through the tar paper in 20 minutes or 30 minutes or 60 minutes, whatever the absorbency rate of that is. So you never want to put that material on horizontal planes. We think of the second plane. The second plane is drainage, but it's also the flashing, and to carry the water that gets behind the wall onto the second plane safely back out. So don't seal the bottom of the flashing. When you put stone on, don't put a mortar space underneath it. Put a plaster stop, just like you do in stucco, to let the water drain out. When you're putting things together, make sure that the water doesn't get trapped and is allowed to escape. When we're talking about the air retarder aspect of the second plane, watch out for the pressure drop when it's sealed. Because the more water that hits that second plane and the bigger the pressure drop at the second plane, the bigger the risk of water entry. Think of the second plane this way. If you put a second plane on that's super airtight, put a drainage plane outboard of that. For instance, if you put a house wrap on, tape the joints, seal them really tight, you still have the potential for the staple holes and other nicks and cuts and things to suck water through. But if you put a layer of tar paper over top of it that acts as drainage, now you've separated the drainage plane from the pressure plane, and then the water will hit the tar paper as well, and hardly any of it will make it to the house wrap that's the pressure drop. Then finally, on the second plane of protection, behind attachments like fans and vents, other openings, other connections, when you have penetrations through there, how do you deal with moisture? Well, the second plane needs to be sealed. And window rough openings, same principle. If you have potential for water to get into the rough opening, how are you going to direct the water that gets there back out? You never want to seal the bottom. You can seal the sides and the top, but don't seal the bottom. We talked about the 4 Ds, deflect it, drain it, dry it, or if you can't do those 3, use a durable material. And then finally, we talked about the Mop Principle, moisture, opening, and pressure. How do we stop water from going into a building? Equalize the pressure, easiest way to do it. We can seal the opening, but equalizing the pressure is one of the better ways to do it. So those are the main principles to think about. So any other questions that anybody has? I think we're right on time here, so we got some time for some questions.
Darrell, we got a couple questions in the chat.
Okay.
If you can bring those up, maybe. It's quite a mouthful.
All right, so let's see here. So from Peter, energy efficiency standards want us to seal the paper, Typar, Tyvek to prevent air infiltration, which is contrary to water infiltration into that paper plane. This can cause water problems in the wall. Absolutely. So if you're planning to use your Tyvek, your Typar as air barrier as well, first of all, use a capped fastener. You can't just staple that in place if you're using that as your air barrier. A cap fastener, when the wind blows, it's going to be on there for a month before you get the siding on. So as the wind blows, and even once the siding on, it can still allow it to move, and that pressure will pop those staples, it'll pop the paper, it'll leave a hole in there. But also never seal the bottom. So when you're putting your air barrier on, for instance, on a wall, if you have your air barrier on a wall and the wind is blowing against it, if you leave the bottom open so that the air can move into it, you've basically created a pop bottle effect. If you take a water bottle or a pop bottle, you empty it out, take the lid off, you have a hole. How much air can you blow into that bottle? You can't, because it pressurizes. So if you think of your air barrier on the outside, it doesn't have to be sealed top and bottom. If you put it on and effectively seal it at the top and effectively seal all the penetrations, the bottom can be open for drainage. And when the wind blows, it goes behind, pressurizes, no more air comes in. So it'll still work. But if you're really worried about it, skip that whole process and go to a liquid applied membrane. A liquid applied membrane is by far the highest performing when it comes to air barrier on the exterior. So you can still pull your air barrier on the inside with your poly and your vapor barrier, but if you put a liquid applied membrane on the exterior, you'll get super airtight. And there's the zip siding as well, or zip sheathing. So maybe you've seen it, the zip sheathing advertised, where they put the sheathing on, it's got a water resistant coating, and they put a tape on the joints. So your framing can be your air barrier too. And that's actually the best place to put your air barrier. So for instance, if you make your framing super tight, your framers are willing to put a bead of caulking under the walls when they stand them up. They put a bead of caulking when you set your floor on, all the joints in particular. And then you came along and you taped all the joints with a material that's compatible with the OSB or the plywood, and you sealed those joints. Then when you put your tar paper on, your air barrier is way back here. Your tar paper is only your drainage plane. And that'll give you a fantastic air seal as well. And that'll prevent suction of moisture coming in. It also helps with condensation issues because the air can't go out. So that's the two ways that I would look at that. So hopefully that answers your question there. One from Ryan Dalglish. RDH did a science paper on the use of excessive non-permeable self-adhered membranes being used on window rough openings that showed potential moisture issues when using an interior vapor control layer at the same time. Do you have any guidance on or suggestions on what you feel would define as excessive use of non-permeable materials? Would it be simply to use vapor permeable membranes and on the head and jambs, and then vapor impermeable on the sill? Well, I think, I haven't read the paper, but I'm guessing that if you wrap the building rough or the window rough opening on the bottom, the sides and the top, like is recommended, I don't believe in that, because that is going to trap moisture. And I do believe, I've seen it lots of times where excessive use of peel and sticks on walls limits the ability for water to get out. So when we're looking at putting a Silpan in, typically I'm not looking at covering the entire bottom plate. Most of your windows are about 2.5 inches from the flange to the inside of the glass. And then the rest is jamb extension. So my rule of thumb is I put the weather barrier in 1 inch inboard of the glass surface so that I'm protecting the bottom. I'm folding it up 5 inches on either side. Then I'm using a house wrap, and I'm folding the house wrap from the outside all the way into the rough opening and then 3 inches inside so that I can tie it to the poly on the inside. So now I can let drying occur at those locations. So when I put the poly on the inside, I terminate it at the face of the 2x6. I don't roll it into the opening. I leave that opening there so that it can breathe. And I put my air barrier about 1 inch in so that that 2x6 in that area can dry and breathe. So I don't know if it answers your question totally, but that would be, that's a very good point. Too much peel and stick, it's going to cause a problem. You can also go to a less, I guess a more vapor open material, like Henry Bacor make what they call a VP100, which is a vapor permeable peel and stick material. You'd have to check the compatibility. You'd have to check, whether you can put it on horizontally. I would assume that that would be fine. But again, it all comes down to moisture in, moisture out, letting it breathe. If you're getting accumulations, letting it dry. Let's see what else we got here. Applied veneer masonry. So lick and stick. Drainage plane on applied veneer stone masonry. I'm a big believer in that, a huge believer in that. You can get some pretty inexpensive materials. Now, it really depends on the assembly. If you're putting windows in that assembly, then 100%, I want drainage plane behind there. If you're not putting windows into the assembly, or it's only going up to the window, my preference is you put a batten underneath the window to allow any water that gets around the window to come down a flashing out over the stone with a batten in between. But if you're putting a full wall of stone all the way to the top, I'm probably going to ask you for an intermediary strip for drainage in the middle. And then I will ask probably for something like a core ply. Haltex, it's a tar paper. It's a corrugated tar paper. It's about 1/8 of an inch. And you just put that on over your tar paper, put your wire on, and that gives you drainage. A cheater trick here that we use a lot is when you're putting stone on and you're only going up, say, halfway up in the middle of a window, but you have a window there, which is a penetration where water can enter. If you take a piece of tar paper before you put your final layer of tar paper on the wall, take a strip of tar paper and fold it, fold it, fold it, fold it, and then staple it under the corner of each window. And then put your tar paper on, put your diamond mesh over top of it. Whatever water gets into that location, if it happens to overflow and get behind the stone, you've given it a natural channel to drain itself right out, and it's free. It's just a matter of fold, 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 staple it on bottom corners. So anything to relieve the pressure and let the water drain out. But again, put the stone on so that you have the casing bead at the bottom. Make sure that that can drain out the bottom of the casing bead, because that's what's usually missing. And stucco, same thing. If you put the stucco on, there's no casing bead, you just end up stuccoing straight to the flashing and no drainage will occur. So hopefully that answers that one. When using moisture absorptive claddings, you can run into moisture driven pressures after the rain gets it. So vapor drive. So with the interior vapor barrier, is the solution to have a rain screen as the best approach? Absolutely. And so what we're talking about here is when you have stone, for instance, and we've seen this where you put the manufactured stone on the wall, you have tar paper, and then you have a regular 2x6 wall. And you're facing a direction where you're getting hit by a lot of rain. So that stone is wet. Now the sun comes out and it beats on the stone. And you get a vapor drive that pushes it right through everything and into the building. So in those situations, you need something between the two that's not overly vapor permeable. So you want something with a low vapor permeability on the wall, but then to let things dry, you need an airspace. So to prevent vapor drive, you put a low, it's still going to be vapor permeable, but it's low, so you're not driving that vapor into the wall. And then outboard of that, you put an airspace between the stone. And that prevents it from driving in and wetting the wall and it'll keep the wall wet almost all summer if you're, depending on how much rainwater you get. So that's a really excellent question. Vapor drive, very common problem. And Lloyd, what is your perspective on cement-based acrylic stuccos? I call those acrylic, or I call those hybrid stuccos. You can't put those on the same way you put conventional stucco on. We get all sorts of failures at battens. We get all sorts of failures at drainage points above windows, bottom of walls, because we don't give it specific enough or enough drainage. So think about the acrylic finish on there. If you go cementitious base and you put a cementitious finish on it, if that assembly gets wet, when the wind blows, it dries it out. But when you put an acrylic finish on it, the wind can't pick up any of the moisture that's in that assembly and dry it out nearly as quickly. Now it's called a vapor permeable acrylic finish, but that stucco gets damp, it gets wet. So the drying potential is a lot lower, the risk is a lot higher. So that means you want really good drainage on those systems. And when you put a batten on there, and then you put the acrylic finish atop the batten, around, underneath, and seal it at the bottom, whatever water gets in typically at the window never gets out. So it means increased vigilance in caulking and sealing around windows, better drainage behind the system, and making sure that the water at the bottom of the system can drain back out. So really good drainage will go a long ways to get rid of that moisture, but it really comes down to your details and how you put things together and whether the water that gets in can get out. It's again, moisture balance. So, and I think those are all the questions I have so far. Those are all excellent questions. Thank you for bringing those up. Any other questions?
Not seeing any. So thank you, Darrell, that was a tremendous presentation this afternoon. That was a ton of great information. We really appreciate you being our presenter today. Thank you to today's event sponsor, the Accurate Technology Group, for sponsoring our virtual technical session today. And thank you to our partners for this month's sessions, the Professional Home Builders Institute. Please join us at our next virtual technical session, scheduled on May 26th at 3 p.m., featuring again Darrell Paul, who will be talking to us about exterior finishings. So thank you all for attending this afternoon session. We really appreciate your support and your participation, and we look forward to seeing you again virtually on May 26th. So until then, stay safe and take care, everyone.